Alright, today this is the last bit of the kinematics, and so we're looking at different expressions for acceleration. So we've used the following. So we've used that acceleration is dv dt, so the rate of change of velocity with time, and also that acceleration is the second derivative of the change in position with time. Now, acceleration can also be expressed as acceleration is velocity times dv dx, and the other one that it can be expressed as is the derivative with respect to x of half v squared. Okay, so proof of these is in your textbook. Page 457, if you are interested in how we can derive these from those. All right, so there's four different things there. And so it'd be handy if we could come up with some sort of table or whatever, so that we could then make a choice more easily of which one we might use. And so this following table helps us decide which one we want to use. Alright, so we're going to be given some information, and the information we'll be given is the acceleration, and acceleration will be in terms of some sort of function, and so it could be a function with time, and that's what we looked at the other day. That the acceleration is a function of time. We could have the acceleration given to us as a function of the velocity. And I'm going to write that twice, because when I get to the next column, it talks about the conditions. So there's lots of conditions that would go with the acceleration as a function of velocity. And then, of course, the acceleration could be a function of position. All right. So, the conditions. So, the conditions would be kind of like at time equals whatever, velocity would be whatever. So here, so if we've got the acceleration as a function of time, the conditions would be given velocity and time. So now we can at a particular time. And so we can anti-differentiate the acceleration to find the velocity function and so on. So if that was the case, that acceleration was a function of time and we're interested in the velocity and the time, then the version of these that we're going to use would be the one we have been using. So you use the acceleration is dv dt. We can then anti-differentiate and we can find the velocity function. All right, so if the acceleration is in as a function of velocity, again we could also be told that the velocity is at a certain time. And again, we would use this same one, the dv dt. Alright, so you can see what you've got: acceleration, time, velocity, and so we've got the one that's got those three things: acceleration, velocity and time in it. Same over here, acceleration, velocity, time, so we use the one which has got those in it. Alright, however, acceleration is a function of velocity. We could also be told the position and the velocity. So it's at a certain position when the velocity is a certain amount. And so we're going to have to use the one that's got the acceleration, velocity, position in it. And so that's this version here. So the acceleration is v times dv dx. And when the acceleration is a function of position, and we've got a position and a velocity, so how fast it's going when it's in a certain position, that's when we use this last version. dx of a half v squared. Alright, so make sure that this is somewhere in your bound reference that you can find it quickly for exam 2. So you can look it up, because it's probably not something that you're going to easily remember. So make sure you know where to find it. All right, let's look at some examples. So the first example is from your textbook, example 21, page 458. So when we look at that, example 21, 458, here it is. Object moves in a straight line, so its acceleration x double dot is given by, so its acceleration, x with the two dots, is given by 1 plus v. Alright, so we know the acceleration is 1 plus whatever its velocity is at the time. Alright, what else have we got? Its velocity at the origin, so it's velocity at the origin, so when x equals 0, v equals 1. And what do we want to know? We want to know, find the position when the velocity is the position when the velocity is 2 metres per second. Alright. Okay, so our acceleration here is a function of the velocity. And what we've got here is we've got x and v. So if we go refer to that table, acceleration is a function of velocity, there's two options here for us. Which conditions have we been given? We've been given x and v, so that's this one here. So we're going to use this version. So we're going to use the acceleration, and I'll use x double dot, is equal to the velocity times dv dx. All right. So, what have we got? we've got that our acceleration is 1 plus v, so 1 plus v then is equal to v times dv dx. We need to get the dv dx by itself, don't we? Yes, so divide by v, so 1 plus v on v is dv dx. All right, now we need to anti-differentiate, but what do you notice we've got here? Velocity, and we've got x on the bottom. So if we're going to anti-differentiate, we need to anti-differentiate with respect to v, don't we? Because that's what this function's got in. So what do we do with this? Flip it, yep. So we flip it, so then v is 1 plus v over 1 plus v, I should say, is dx on dv. And so now we can anti-differentiate both sides with respect to velocity, and that will tell us the position. All right. Looks like a B, not a V, doesn't it? Anything there anyone likes the look of? No, no one likes the look of anything there, fair enough. All right, I'll rub this bit off. All right, so we need to do something with this because we've got a V on the top and a V on the bottom. What do you notice about the highest power of V on the bottom and the highest power of V on the top? It's 1, it's the same. So a thing that you can do is if you've got a power the same or higher on the top with your variable is on the bottom, you can divide. Or 1 plus b, whatever. So, to get v here, we need to times by 1. So then 1 times v is v, 1 times 1 is 1, and then we take that stuff away, and we get -1. Yes? So what that tells me is that v over 1 plus v, or v plus 1, is the same as 1 minus 1 over 1 plus v. Yes? No? Maybe? So now I'm going to replace. So now I'm going to say, all right, well, let's look at the antiderivative. And that's equal x. So now, hopefully, we should be able to do this. Again, it looks like a b, not a v. Antiderivative of 1 is v, yep, minus what? 1 over, first thing we think of is, starts with L, pretty cute, log to the base E of 1 plus V. And I probably, to be strictly assured, put those magnitude signs in here. Plus some constant equals x. All right, we'd like to know what that some constant is. And fortunately, we were given some information, and we were told that when the velocity was equal to 1, x was equal to 0, or the other way around. So I can substitute that in. So 1 minus log to the base e of 1 plus 1 plus some constant is equal to 0. So our constant would be log to the base e of 2 minus 1. So that means then our position would be v minus log to the base e of 1 plus v plus the constant, which is log to the base e of 2 minus 1, and that's what x would be. Alright, then it asked us to find the position of the object when its velocity is 2. So, when the velocity is equal to 2, we make our substitution. You get that. 2 minus 1, of course, is 1. Now, what about this stuff here? This stuff here I've got negative log to the base e of 3 plus log to the base e of 2. What can I do with these? 2 over 3. Alright, there's a negative in front of this. Alright, and this negative in front of this here puts the 3 down the bottom, so therefore it's plus here. Alright, so there's that. Anything about that? Alright. Let's do another, excuse me, another example. I'll rub that off. Alright, the next example we're going to do, again from the textbook, 22, page 458. Let's go where it is, 22, there it is. Particle is moving in a straight line, its acceleration is a metres per second. A is negative square root x. Alright, so we've got acceleration as a function of position. What else? Whereas position is x, find the relation between v and x, which describes the motion. Given that v equals 2 when the particle is at the origin. So v equals 2 when the particle is at the origin. So if the particle is the origin, x is 0. Alright. So acceleration is a function of x. We've got v and x. And so this is the version we need to use. So we've got to use the acceleration as d dx of a half v squared. So, negative x to the half, I'm going to write it as, is d dx of a half v squared. Alright, we're already on the left over here, got it in terms of x. Going to anti-differentiate with respect to x, that's all good. So, antiderivative half with respect to x, and of course when I do this side I've just got the half v squared. Alright, the antiderivative of negative x to the half is what? Negative x to the 3 on 2, divided by the new power, divided by a fraction, turn it up, down, multiply, yes? I'll do all of that at once. Yep. Oops, forgotten the constant. Alright, we were given some information. We were told that v is 2 when x is 0. So if x is 0, v equals 2. Stick that in. Put 0 in here, you get 0 plus c is a half of 2 squared. So z is c, not z, c is a half of 4, which is 2. So, that tells me then that a half v squared, I'll put that at the front, is equal to, I'll put the 2 at the front, 2 minus 2x to the 3 over 2 on 3. Do I need to rearrange that or don't I need to rearrange that? Let's see, what does it ask me? Find the relationship between v and x. Well, there's a relationship between v and x. But let's just neaten that up a bit by getting rid of the half there, multiply everything by 2. And so v squared is 4 minus 4x to the 3 over 2 over 3. And so we probably just leave it like that. It just neat as anything. Right, anything about that one? No? Alright, one more example. I did these out of order. I don't know why I decided to do these out of order. But anyway, must have had some reason that I thought of at the time. So we're going back here to example 20. I didn't do them in order, but anyway, not to worry. So example 20, in your textbook, page, whatever page it is, 450 something, 7. Alright, let's have a look. So, an object travels in a straight line such its velocity is, so we've got v squared equals 4 minus x squared. Find, oh that's why I did it, didn't I? Sorry. Find the acceleration at x equals 1. So we want to know acceleration when x equals 1. Alright. Alright, so when we have a look at this, we've got v squared on this side, and we've got 4 minus x squared there. No acceleration going on there. So we've got to have a look and we've got to think. So when we look at what we've got here, two of these versions, even though we haven't been given an expression for acceleration, we're going to look at these. Two of these versions of the acceleration are looking at derivative with respect to x. Alright, and so when we have a look at this and we look at this one, okay, so if two of those versions have derivative with respect to x, well, there's an x there, that's all good. Notice here we've got a v squared, yeah? This version here is the derivative of the v squared, yeah? So, I'm going to do it differently to the way that they do it. If I times a half both sides, because I can do anything to both sides as long as I do it to both sides, yeah? Yep. If I then say, okay, because it's asking for acceleration, and I know that if I differentiate half v squared with respect to x, that's going to give me acceleration. So let's differentiate both sides with respect to x. So the one we've got here on the left-hand side, well, it's now simply acceleration. I'm going to expand that bracket before I do the differentiation. Half of 4x2 minus a half x squared. Differentiate that, what do I get? 2 becomes 0. Minus 2x, or minus x I should say. Minus a half times 2x. Negative x, yeah. And the question asks us to find the acceleration when x is equal to 1. So when x is equal to 1, the acceleration then would be negative 1. I think it's metres per second squared. Metres per second for velocity, so metres per second squared. Alright, anything about that you want me to further clarify, give you more information? Alright, so yeah, I just looked at these things here and compared these and seen what ones. This one's got the v squared in it. Let's make it look like that because we want acceleration. So that's what we did. Alright. Done.